In the previous topic, that it was titled Orthonormality and the Method of Finding the Coefficients here, we had the Fourier series representation with the functional basis as the unit step, the cosine representation, the sine representation with the modifications which are satisfying the condition of orthogonality as well as the condition of orthonormality here. Now, the complex Fourier series representation as alternative representation to the earlier one that we have seen in the previous topic we can do. So thereupon the use of two most important formulas what we can recall as the Euler's identity. We have sin omega t expressed as e to the power j omega t minus e to the power minus j omega t divided by twice j, where j is the imaginary factor or the variable we call upon with the value under root minus 1 in the complex domain. Next to that we have the formulation cosine omega t, that is equal to e to the power j times omega t further added by e to the power minus j times omega t, and this addition is divided by 2 as a constant here. So by using these two formulations for sin omega t and cosine omega t, when we have the series representations as a1 cosine omega t added by b1 sin omega t, the use of this formulation we can have on the right hand side represented as a1 minus j times b1 divided by 2 multiplied to e to the power j omega t, and this term is added to a1 plus j b1 divided by 2 into e to the power minus j omega t. So if we have the representation of a1 minus j times b1 divided by 2 as capital C1 and a1 plus j times b1 divided by 2 as c suffix minus 1, so that time the alternative representation of the Fourier series we can give, and this is with the help of complex exponentials. So the generalized representation of any signal f of t into the defined functional space, we can have f of t is equal to capital C suffix 0 further added by capital C1 e to the power j omega t added by c suffix minus 1 e to the power minus j omega t, and this addition continues with the components like capital Cn into e to the power jn omega t added by c to the suffix minus n into e to the power minus j n omega t, and so on here. So finally we can also have the simplified representation. So f of t will be equal to the summation for n is equal to minus infinity to plus infinity capital C suffix n into e to the power jn omega t. Now one important thing we can make noted here, that this formulation of the complex Fourier series is having the complex exponentials and the concept of negative angular frequency denoted by minus omega here. So practically there is nothing imaginary in any of the signal and there is no negative frequency. Here the complex exponentials into the use of this representation helps us or facilitates us for easy manipulation of the multiplication and the integration operations those are involved in the computation or the calculation of the Fourier series coefficients than the multiplication and integration using the plain sine and cosine functions here. So if we first of all try to visualize the complex exponential e to the power j omega t, where omega is equal to 2 pi divided by the time period capital T. So here we have the de Moivre's formulation e to the power j omega t is equal to cosine omega t added by j times sine omega t. So here we think of this particular functional representation as a bundle of sine and cosine functions kept together side by side such that they do not mix with each other, and the function of j can be thought of as a separator indicating that the two parts, namely we have the cosine omega t and the sine omega t, are satisfying the condition of orthogonality. So this was a brief discussion with respect to the complex Fourier series. So this is really very important while we switch from the Fourier study to that of the Wavelet study here. So this will have building a strong foundation before entering into the Wavelet domain. That is why this was the topic covered in this particular current chapter.